Okay. Okay. Good. So we know, in addition to that, when we quantify the correlation coefficient as a marker of the strength of this association or correlation, this can take a negative value of maximally -1 and a positive value of +1. So this correlation will somewhere be in between. And the absolute value of this correlation coefficient essentially determines the strength of this correlation, independent of its sign. Its sign will only give you the direction of this association, which can be either positive or negative. So this being said, we basically look also at +1, we're looking at a perfect positive correlation. And at -1, we look at a perfect negative correlation. The increase of the negative correlation coefficient or the decrease of the positive correlation coefficient, so everything going towards 0, will essentially show a weakening correlation. Correlations are quantified in the correlation coefficient that can be categorized into small, medium, large correlations with the thresholds of 0.1, 0.3, and 0.5. Don't be misled by the sign. It's the absolute value that determines the strength of a correlation. So that's like one of the trick questions you will find quite abundantly in the quizzes. Misleading correlations are correlations that are to be taken very cautiously and to be recognized. So you need to understand if a third variable basically associates with exposure and outcome and thereby causes the spurious correlation. Important is to keep in mind that when you have a sample that you're analyzing, the R will indicate your correlation coefficient, whereas in a population it's rho, which is the Greek letter for R. The correlation coefficient is basically calculated with two separate components. One is the sum of the product of all deviations, which basically is here the numerator in this calculation, which basically gives you the sign. Whereas the denominator here is the square root of the product of the sum of squares of x and the sum of squares of y, which basically gives you a marker of this variability. So the strength of this association is mainly determined by the variability between x and y, whereas the sum of these two as a product gives you essentially the direction. So this is the directional component. So it's important to start with a scatter plot, and that's in essence, a scatter plot is a very elegant way to depict data, and you will find this quite frequently, and it's one of the most frequent graphs essentially in science. You will basically reflect on this graph an association, and you will see x as well as y in one point. So each of these points is one individual. So when you have the scatter plot for our students' absence and grade example, you basically see each point represented by representing one student. The calculations we have gone through, so you basically calculate the deviations and you sum the product of these deviations up. Then you calculate, just like we did before, the sum of squares of x and sum of squares of y. And basically you have a built-in standardizations by doing that. So you get this sum of products of the deviations and you standardize it by the square root of the product of the sum of squares x and y. This gets you the correlation coefficient. Then we have partial correlation, and this is basically when several variables lead to one particular association, and this is important to keep in mind in the context of a Venn diagram. So the Venn diagram basically shows you overlaps in the predictive qualities. So you basically, if 1 and 2 and 3 variables come together, they basically where they're overlapping. This is basically where you have a joint correlational effect. This is important to keep in mind also in the context of psychometrics. So psychometricians, which are basically experts in survey analysis and survey development, So they basically focus on reliability and validity, where reliability basically means that a survey that you're doing on one day should also yield the same result for the same individual the next day. So that means that the result you're yielding from your survey is basically reliable and consistent from one day to another. That's a test, retest reliability. Another possibility, if you only have one survey of one individual or several individuals, you should basically be able to correlate items within the survey. So one way to essentially test for this reliability is by doing a split half reliability, where you basically take odd numbers and even numbered items, and the results of these items should actually correlate at a certain high level. So they would be highly correlated if that test indeed tests for what you want to test, and no item basically is deviating from the accuracy of predicting that outcome. Reliability can, for a sample, also be quantified as a so-called coefficient alpha. That's symbolized as an alpha, and it's also called a Cronbach's alpha. That's basically you get the mean result of these split half correlations, and you are correlating these over a whole population. And for a survey adequately used in a population, this should basically exceed 0.75. Validity in the same context is basically meaning that the survey is testing what it indeed is meaning to test. And that's particularly in some of the more mainstream and popular magazines shown quiz is not necessarily the case. So these are to be taken with cautiousness. In clinical medicine or in clinical routine, you use these surveys essentially, and you test and you corroborate the validity by basically associating the results you get for patients with clinical outcomes and clinical characteristics. So if, for example, somebody reports in a quality of life survey that he or she thinks their health is not really that great, this should hypothetically correlate with a metric like, for example, the number of hospitalizations that individual went through. So you would test for validity by testing it and associating with clinical outcomes. Any questions on correlations? It's considerably simple, right? It's quite intuitive and simple also, and it's calculation. If no question, then we can move on to regression, which is essentially the continuation of correlation. So this is basically where we enter the next stage, because now we're not only establishing correlation and association, we also need to predict variables. We're predicting a dependent variable based on the values of an independent variable and the development of a so-called model. And this model will basically be a linear function, and we've done that in the last class. So it's basically predicting a dependent variable based on the independent variable, but basically taking the standardized values for the x variable, for the independent variable, multiplying it with the r's and with the r, with the correlation coefficient that we've quantified in that fashion that we have discussed just before, which basically determines the strength and the positioning of that function. And thereby you can basically predict standardized y hat values. Y hat basically is a predicted value for the dependent variable. And it will take, so y hat essentially is then allowing to derive a linear function. And this linear function basically can then be utilized to quantify each individual y hat. And we have done that in last class. What's important for this determination is that you have two components in your linear function. You have an intercept, and the intercept by definition is the dependent variable, the value for the dependent variable, where the line crosses the y-axis and x equals 0. Whereas the slope, by definition, is the change, increase or decrease, of the dependent variable with 1 unit change in the independent variable. And this slope you multiply with your individual x. So if you remember, and I will go back to the spreadsheet now. If you remember last class, we basically did, don't need that. If you remember from last class, what we did was we calculated, based on number of stressful life events and back depression inventory, we calculated the product of deviation, which is basically the deviation multiplied of x multiplied by the deviation of y. We're summing this product up, and this gives us that product. Then we calculate sum of squares, and that gets us to the R, to the correlation coefficient. And then, and this is really what's important to keep in mind here, we utilized now this knowledge, this correlation coefficient, to derive from standardized x values. And we have taken arbitrarily 3, 2, 1, and 0. So keep in mind, we're looking at back depression score as a function of number of stressful life events. So we took 3, 2, 1, and 0 stressful life events. We standardized this according to the mean of x, which we knew was 1.9 stressful life events. We standardized it by calculating the individual x, 3 minus 1.9 divided by the standard deviation, which I forget what it was. But basically, we're standardizing it by division of the difference between the individual point minus the mean by the standard deviation. So we get 4 different entries. We get a corresponding set of an x of 3, a corresponding set of an x equals 2. And then here was the mean at 1.9. So basically everything below 1.9 is a negative value. So it's just a classical standardization that we did in previous classes. I think chapter 6, if I'm not mistaken. So by utilizing now the correlation coefficient, we can now calculate a standardized y hat. So it's basically just calculating, multiplying the set x with the correlation coefficient gets us to a standardized y hat, which is a predicted standardized y hat. And taking the mean of y, the actual observed mean of y of 15.7, we just have to calculate back, right? So we have a standardized y hat. We're multiplying this with the standard deviation, and we're adding the mean. We get to our original score of y hat. And this is what we did right here. And so we know now that our predicted y hat for 3 stressful life events is 19. And this is exactly where we are here. Then we have 16, which is right here for 2. Then we have 12 or 13, which is right here for 1. And we have here our intercept of 9.542. So this corresponds exactly with those metrics we need, essentially. So we have our intercept already here, which is 9.542. And now the slope can easily be derived by just calculating the difference of one value minus the other value that is numerically 1 unit less. So that's the difference between y hat at 2 stressful life events minus the y hat at 1 stressful life event gives us the slope. Whereas the slope, as per definition, is now the increase by caused in the increase of the dependent variable caused by an increase in the independent variable by 1 unit. So this can also be done by calculating y2 minus y1 divided by x2 minus x2. So hypothetically, this is the formula how you calculate slope, and you have done that in high school, right? So this is basically a y2 value, which could here be 12, minus y1, which is here 9.5. The difference is 3.24, divided by x2 minus x1. x2 would here be 1, minus x1 is 0. So it's 3.2441 divided by 1. And so that basically gets you to the very same slope. This is just a calculation how it's mathematically derived. I did a little bit simpler here, but you can do this in the proper way. Based on that, we went then on to calculate our actual y hat. So now once you have this formula, you can actually predict for each participant in your study a predicted dependent variable, a predicted y. So we did that by calculating the number of stressful life events for each individual multiplied by our slope of 3.24 plus the intercept of 9.54. That gets us to a predicted y. And so now the next step in this is to essentially quantify, I just want to quickly show that, the predictive quality of this prediction. How good is my prediction? So obviously every prediction has its inaccuracy, has to be, right? Makes sense. So we basically, when we look at these two graphs, we clearly see, and hopefully this is obvious to everybody, is that the left graph shows a much better and more accurate prediction, because A, the points are less far apart, and this will just be much more accurately reflected by that function. Whereas here on the right graph, you see that the distance between the individual observation is basically quite far. That means that that prediction can never be as good. And this essentially is one of the problems that is often caused by additional confounding factors. And this is what multivariate regression, for example, wants to factor in. So one way to quantify that is essentially to calculate the reduction in error. And now let's go back to the spreadsheet, because in the spreadsheet you have here now exactly that calculation. And we did that in last class. So we gotta keep in mind that there's a total variability. There's a variability after employing that function. So that is left after that function was actually employed. And then there's a predicted variability, the error that the regression function actually can predict. And this is nicely depicted here in this graph. So when we have a sum of squares, a total sum of squares, a total variability, a total error, we're basically testing a dependent variable, a mean of a dependent variable. And we're testing with our sum of squares total, the difference between each individual point and that mean. So we have calculated this. When we calculated the standard deviation, we did exactly that. We calculated the difference, we squared the difference, and we're summing these squared differences gets us to the sum of squares. This is essentially what this shows. This shows here the individual differences of each individual observation from the mean. That's our total variability. If we're employing now our function, our regression model, we're essentially seeing here minimized differences between the individual observation and our model, because the model is fitted in a way that it minimizes these differences between the individual observation and the predicted value. And this is reflected by the fact that if you calculate this by estimating for each individual the dependent variable, then calculating the residual error, and this is column I in the spreadsheet that I've sent and shared with you as an announcement, and we did last class. You get a residual error, which is the difference between the individual observation and your predicted line. You square this difference, you basically get here in the end, after summing it up, you get a residual error. You get a sum of that squared residual error, which is essentially smaller than your total variability. That means that your prediction with your regression function is improving your predictive accuracy over just taking the mean. That is the interpretation of this. And if you calculate now the difference between your total variability and your sum of squares residual error, you basically get a sum of squares regression. And this is basically the explained variability in your scalar by your regression model. And if you're taking now the next step to quantify the proportionate reduction of error or coefficient of determination, or just simply R squared, you're basically calculating a proportion of that explained variability, the sum of square regression, as a proportion of the total variability. And that's 0.33 here. Of note, this is all of this is consistent with what Excel produces here, which is the quicker way, but this is the arithmetically, and that's the conceptual way how to get to that. Good. So now let's move on from that. Any questions to that? I think it's quite logical, right? And stepwise, it really gets us to where we want to go, because now we want to improve our accuracy. And this is where we're getting to multiple regression. And we have determined with multiple regression that we can improve this explanatory power of our model by including additional variables, because it's not only one variable explaining a dependent variable. That makes sense, right? Even if there's a very tight correlation, there's usually always something else happening. And Norton and Heinzen is provided here with the data of sleep disturbance scores. So if we just copy this over in our Excel spreadsheet, oops. So if we're copying this here, we can now take here our individual participant ID, the number of stressful life events, and the back depression inventory score. We get now a data set that is consistent with what Norton and Heinzen shows in the PowerPoint. So now employing a multivariable regression, and we will do it in R in a second. If we are employing a multivariable regression on this model, we're getting this output. So this is in SPSS, and R will have a comparable output. So the components will be the same. So you will recognize the same components. It looks a little different, and R doesn't show the standardized coefficients because essentially these are not as insightful anyways, but it will show you in the same format. It will show you a constant or intercept, and it will show you the individual variables, and it will show you the coefficients or estimates. It's actually an estimate rather than coefficient. So you have here for, if you include both of these variables in your multivariable model, you get an intercept of minus 4.117. You get life events 1.194 as your slope, and you get 2.09 for sleep problems. You get a corresponding standard error. You get a corresponding t-score that will allow you then to quantify the p-value. So this again follows a t-distribution, because again we have small sample sizes, but basically follows the same rules as the t-distribution. That will also allow you to derive then your p-value. So if you use this model now, and this can be used in the very same fashion as your univariate regression model. So let's just copy this in here. So we have now an intercept of minus 4.117. And in essence, what the formula will look like to depict, to predict your dependent variable will be minus 4.117 plus your 1.194 multiplied by your life events plus 2.089 multiplied by your sleep score. So this is the formula that basically will allow you to predict your dependent variable. So this is how you calculate your depression score. So it's nice, right? So you essentially you can you can use your insights from your population to essentially calculate your y hat now. And this is now minus 4.117 plus 1.194 multiplied by life events, which is in column B, plus 2.089 multiplied by D2. So that's your y hat. So now next you want to know your residuals. And you see already with the naked eye that your residuals are substantially smaller than they were before. So when you look at the residuals here, they were substantially larger. You basically had residuals errors somewhere in the range of like 10 to 7. So they are getting substantially smaller here with 2 variables predicting your dependent variable. Squaring those residuals is basically corroborating this insight and leading to a substantially smaller sum of squares. And this is again our sum of squares of the residuals. So this is now not 526 anymore, but it's now 79. So that has substantially improved the accuracy of our prediction. So if we, in the next step, so we have now, well, let's copy over our sum of squares y. That's our total variability we said, right? So we have now our total variability, which is the sum of square total. We have a sum of squares of the residuals, so that's the residual error. We want the sum of squares regression now, which is what our regression function has now explained, which is essentially calculated as this minus our residual error. And our sum of squares regression is essentially here 1850. No, that can be. Huh, look at that. Look at that. Oops. So 788, 78. Okay. So you shifted my column. Okay. So we have now a sum of squares total of 788.1. We have a sum of squares residual of 79, and we have a sum of square regression of 708. So keeping in mind now the calculation of the R squared, which is quantified as the proportion of explained variability of the overall variability. So if R squared equals sum of squares total minus sum of squares error divided by the sum of square total. So this is the proportion of the overall variability that was explained by our regression model. And calculating this here would result in 788.1 divided by 708.88. And that, oops, the other way around. Oh, here, it's late. E13. Okay, so we have now brought our R square of 0.33 from our univariate model to 0.89 in our multivariable model. So that would kind of suggest that including sleep disturbance score essentially massively improved the accuracy of our prediction. And that's also what we see because, oops, that's also what we see because when you look here at the p-values of our model, the one that actually is the only variable that is significant, the only quote unquote predictor that is significant is our sleep problems. And also here in regard of our coefficient, this is also the most weighted coefficient. So this being said, this is how you utilize a multivariable regression model to predict dependent variables. Any questions to that? I know it's maybe a little much, but I think the concept is kind of clear, right? So you essentially, you're utilizing however this multivariable model was determined by taking all these factors into account and kind of shifting variables in a certain shape or form, allows for us now to improve our prediction, lower the residual error, increase the variability explained by the model, and thereby increase our proportionate reduction of error quantified by the R squared. Any questions? Okay, then I've lastly, we talked already about this last time. So just, I think that multivariable regression and the understanding of the principle of multiple regression is quite central because it is everywhere in your life. It's literally everywhere in your life. It's on your phone, it's on your computers, it's on your shopping behavior is being quantified when you print out coupons at the grocery store or at the pharmacy. So all these models basically derive all this information that you have provided to it, passively or actively, and it will use it to predict your future behavior. It will forecast your shopping behavior. It will facilitate aspects like anticipatory shipping, which is, we talked about this delivery within 1 day. It will only be possible if you have such predictive models that allow to facilitate life. Good. Any questions? If not, then we can open R. And we will today do the very same examples that we have done in Excel now using R. So if you open module 22 on Canvas, or 23, is it 23 or 22? You will find an R script that is called Practice Lab 5 initial R code, initial code R. And this is the code that it is actually, no, it's 23, lab day, module 23 lab day. So this initial code, basically, you just need to read into your R. So you go on File, Open. You find it in the respective folder, and you just start it and load it. So what we're doing here is pretty much consistent. Line 2 is consistent with what we've done in the past. So it's basically just cleaning the environment. That's all you're doing here. Essentially, okay, to those plots we come later. So we have essentially, and this is consistent with the exercise listed in the Word document in Practice Lab 5, you have two examples. We have the module 21 example, and we have the module 22 example. So these are, they're labeled a little different. So we are actually one class ahead. We have one more than the other class last semester. So we have now DFM22 is the data set for our correlation example. So DFM22 was the example with 10 students with their absences quantified and their corresponding grades. So the idea here was to see whether absences do predict grades or associate with grades. And we can do that analysis now with two steps. So we first do a correlation analysis, we quantify correlation coefficient, and second, we develop a simple linear regression model. So line 7 will basically give you a list of variables included in your object. So this is your absences, grade, and students, which is consistent with what you see when you click in it. So you click and activate it by clicking on this little tab on the side. you can then open it and look at it just like you would see it in Excel.
Yeah, I have a question, sorry.
Yeah.
Were we supposed to run it until 7, like up until now?
Yep, you can run.
It until 7?
Yep, you can run line 2 and then line 4. You just press Control Enter twice.
Wait, just 2 and 4?
Mm-hmm. It will automatically run the entire 3 lines. So basically, when you run one command, it will automatically recognize that all of this is one command. So this basically, this is one line. It's just tabulated and broken into different lines. So once you have DFM22 loaded, you can look at the variables included in DFM22 with ls, which gives you a list of sub-objects contained. Then you can run line 8, which is basically giving you just one variable in your object. With the $sign, you basically attract specific objects, specific variables in your object. So this is your data set, and you just run a specific variable in your data set. So if you do DFM22 $sign absences, you basically extract only that variable from your object. If you want to pack now your variable absences into a separate file, and you want to pack it into not file, a separate object, you can do that. And this is line 9. Line 9 essentially becomes now and develops absence as a separate object containing exactly these 10 entries that derive from DFM22 $absences. So basically it just takes the variable and packs that as an independent vector into an additional object. The reason why I'm showing you this is because it's sometimes in some situations it's quite useful to know how to do that. We can do the same with grades. That's now we can change this to grades. Actually, that should be grades. And now we're only addressing the grades in line 10. Having changed the absences into grades will allow us now to create an additional object labeled grades with 10 different entries that are consistent with DFM22 grades. We have now next we can calculate with the core function COR. We can calculate the correlation coefficient. In line 12, you're basically packing, and you're packing this correlation, this result of the correlation function into an additional object. And whenever you want to place some output or any model or a data frame or whatsoever into an additional object, you will do that by stating this sign, which is a smaller sign and a hyphen, that basically will then pipe your whatever you want to pack into that object. So you're developing a new object now that contains only one value, which is the correlation coefficient. So CoF1 from now on will basically just contain one number, which is minus 0.85, which is the correlation coefficient of our absence example. So if we would go now in the console and we write here CoF1, it will automatically recognize CoF1 that we just want that correlation coefficient of minus 0.85. So we can call this object whenever we want to call it. If we go now in line 13, any questions so far? Yep.
On the blue line where it says M22 $99 mine says M22 minus 4 in absence.
Which one?
Like the first of the 3 blue towards the bottom.
That could be because I changed this when I changed line 11.
So if mine says absence is on pair, should I change?
Yeah, we do in line 9, we do absences, and then line 11, we do grades.
Yeah, mine says absences twice.
Yep, I'll just change it to grades.
Okay, so should I change mine to grade?
Yeah, let's change it. Okay, line 13 then essentially introduces a new function now. LM is a function that allows for you to build a linear model. So like all the regression models we've done so far, essentially are nothing else but linear models, right? So we're only quantifying linear associations and linear relationships. So LM will develop a very simple regression model. And you are essentially feeding two variables into this model. You have one dependent variable, which is your grade, which is DFM22 $grade, followed by, and I'm flagging this because that's a very important symbol that R will need in a couple of different situations. That's the mathematical tilde. The tilde is basically seen when you look at your button one on your keyboard. You have right next to it, to the left, you have the tilde. You have apostrophe and you have tilde. If you press shift and apostrophe, it will give you the tilde. So this is how you can actually type that. So, but you have it already in the code, so you don't need to type it again. But basically, you have the dependent variable first, then the tilde indicates that everything in the following is basically the list of independent variables. So you have dependent variable as a function indicated by tilde of your independent variable x absences. So when you run now this code, and again, we're packing this linear model here into fit1. So if you run this line and make sure it's not selected, nothing is selected, just click into the line, click into line 11 or line 13 and run it. You basically get a new object here in your environment. And this object is fit1. Fit1 is basically your linear model, and it contains everything that pertains to this linear model. And that's the beauty of R, because it was in the click of one button. You have a plethora of different information for your model. And we're going to look into what is all contained in fit1, because fit1, in summary, fit1, you basically get, and that's line 14, you basically get a printout of all the information that is relevant for your regression model. And the first aspect is here. It gives you with core, it gives you basically the formula again. So the formula is DFM22 as a function of grades. Then we have, secondly, we have the residuals. And remember, the residuals is the difference of the individual observation to your predicted value. So these residuals actually follow a normal distribution around a mean of 0. So now the million-dollar question is, there's no mean, but there's a median. The median is negative. What does that tell us? It's a normal distribution. It's supposedly a normal distribution. The median is smaller compared to the mean. What does this mean? In which direction? Very good. But which direction? Almost. Positive. And why? Why? And that's important for the final. I'm flagging this. It's make sure you understand this, because you remember when you have outliers and you have skewness, arithmetically, it will always affect the mean. And if you add more to a sum and you're dividing by the same number of entries, this will shift the mean to the positive if the outliers on the positive side. If they're on the negative side, they're negative. So it will shift it positively. The median doesn't move as easy. The median is considerably resistant against outliers. So now what you have, the median is smaller than the mean, because the mean is 0, because that's how it was fit. Because the fit that you have created in your line of best fit, or fitting your function through, is based around the median, because we have standardized and we have predicted, standardized, predicted wise, based on the standardization of our X. So this being said, the mean is 0 of all residuals. And the method that was being used is actually has a name evolving around that. It's called the least square fit. So you that you fit that based on least square. So you minimize and you find the least square, the least sum of squares. And okay, so we have so the mean is larger than the median. That means it's positively skewed, so it's skewed upwards, right? In the prediction, you have the line there. So basically, the residuals are skewed upwards. We have here, in addition, with Q1 and Q3. Why is this important? What can we calculate with a Q3 minus Q1? Interquartile range? Yes, perfect. Thank you. And we have minima and maxima. So that already points out it's just larger on the upper end, right? Then we have the coefficients. So the coefficients are basically the same as we've seen in the SPSS output. We have an intercept, which is labeled as constant in the SPSS for whatever reason. Then we have the variables that are included in our models, which we only have absences. And this is our estimate. So if we want to estimate now an exam grade, and we have an individual that never missed class, what is that individual's grade going to be? If you look at this model, if x equals 0, what will the grade be? 94, exactly. It's the intercept. If the individual misses now one class, what's the grade then? Yeah. Yeah? 89, yes, approximately, give or take. Yes, exactly. So you can calculate and predict now by taking the intercept and you subtract this multiplied by the number of times that individual has failed, missed class. Okay, so then we have a standard error. That's basically the variability around that estimate for each of these variables. And then you have a t-value that basically is a resultant of the standard error, as we know, because that's the difference between the estimated value and the actual observation, standardized as per t-score. Based on the t-value, we get a p-value for each of these variables. We see that this is a significant relationship because the p-value is smaller than 5%, which is our acceptable alpha, or type 1 error, aka alpha. Then we have a residual standard error, so that's for the overall model. So this is using the standard deviation of the standard error of all the predictions and all the observations on 8 degrees of freedom. Keep in mind, the degrees of freedom in a correlation is the sample size. So you have 10 students, you have 2 variables, and you calculate 2 sum of squares. The resulting degrees of freedom are 10 minus 2 for 2 sum of squares. And that's a trick question. I need to make sure that you don't trip into this trap. If you are asked the degrees of freedom for a paired sample t-test, the degrees of freedom are essentially your individual differences minus 1, because it's only one difference. If you have an independent sample t-test, you calculate the degrees of freedom independent for each sample. So that's minus 2. If you have an ANOVA, it's the overall n minus the number of groups. If you have a correlation, it's the sample size, the number of participants, minus the number of variables. Because that's the degrees of freedom that you're dealing with in the overall model. Because the F statistic that corroborates and calculates then the p-value of your accuracy in the overall model is based on 1 degree of freedom between group in the numerator, which is 1 variable, and, oh no, it's actually 2 minus 1 because it's an intercept and 1 minus 1, and the 8 degrees of freedom in the denominator. So that's between groups and within groups. And this is the intersection. This is beyond the scope of this class. This is the intersection between regression and ANOVA, because you can basically do, you can utilize a regression model to replace a t-test. You can use a regression model to replace an ANOVA. But that's more about that in your future statistical education. Okay, but this is basically all that R offers, which is quite a bit. You can additionally look into LS fit 1. You get additional variables. You can have all these different pieces of information from your model. All of this is packed into your fit 1. If you do LS summary fit 1, you get all that are basically part of, you get covariation, you get R squared F statistics, you get details on the F statistics. So you can study all of that, and you can play around with it. It's quite insightful. Then you have, yep. Next, 15 to 17, line 15. The last thing was LS summary fit 1. So it's just, so you remember how we did summary fit 1 and we got the summary of the model?
You do summary fit 1 again. Yeah.
Well, sure.
Like where you typed it in, you just have to press enter.
Yeah, summary fit 1.
And actually, you should just type in or there's something to run.
Well, you can just type it in. Well, summary fit 1 is always on line 14. Yeah. Yeah.
And then what do we have to type in?
You can do LS summary fit 1 gives you a list of all information, all pieces of information that are contained in summary fit 1.
And that's just for us, or like you want to see that in what we do?
That's just for you.
Okay, so I don't have to have that in my
thing. That's fine. But you can't do it.
Okay.
Yeah, it's yeah, I know. So yeah. So again, it's like some of this will not be necessary for you, but if you go further and you will find yourself doing statistics one time in your life, this information can and will be important. Good. Line 15 to 17 is basically building a scatter plot. And this kind of like emphasizes that R has really a nice graphical engine. Does actually really pretty graphs, and they're very customizable. So you can do a couple of things. You can have text anywhere, you can have legends. So it's really very nice and versatile what you can do with it. It's basically what you have is like you have this plot. You're basically plotting whatever you want to plot. You can manipulate the titles, the axis titles. And of note, and that's the beauty of R, whenever you change now your data, you don't have to change the code. You just have to rerun the code. That's quite important to keep in mind because sometimes this causes additional work if data changes or some additional data is collected or whatsoever. Good. Yeah, so with plot, you're actually plotting your scatter plot. With airline, you're basically fitting a line through. And that line is consistent with your function fit 1. And R will automatically recognize that you're interested in plotting your line of best fit. And then you basically with text, you're just adding some text, adding the correlation coefficient here after a comma. But again, this is if you play around with it, you will see what that all entails. Line 19 to 22. So that's kind of our correlation example. Any questions to that? I think it's simple to run. It's quite intuitive what to do, right? Yeah.
Mine is like saying that plot time name has not
Okay. Can you write the following? dev.off and parenthesis open, parenthesis closed.
Then click enter.
Click enter. Do that twice now, just one. If you run it now again, it should work. If you run line 15 to 17 in one, it should show you the scatter plot now. Yeah.
After you do that, then what do you click?
You just run line 15 and 17 again. So device off means that you're shutting off the graphical engine of R. You're just clearing.
Not 16, just 15 and 17, or also
15 to 17, including 15 through 17, I think is the problem.
what if I'm still getting the error?
Well, then we need to look at it after class. Okay, line 19 to 22 is now creating an additional object, which essentially is now the same as we had in Excel, including the sleep disturbance score. So we have the individual ID, we have events, which is the stressful life events, then we have the back depression inventory score, and we have the sleep disturbance score. And if we want to correlate now our BDI score with the events, this is line 23, gets us a correlation coefficient, right? That correlation coefficient is CoF2, which is our 0.58.
Should you run line 18 even though it's late?
No, you don't have to. Okay. So that's CoF2. Then we have in line 24, we're running our first regression model. That's Fit2A. Fit2A is basically following the same outline as the previous model we built. Fit2A is basically the back depression inventory score as a function of the stressful life events. We know the outcome of this already. It's consistent with what we calculate in Excel. This time we also see our residuals. We see that this was a fairly accurate model. We see our intercept of 9.54. We see our slope of 3.24. If we go now, summary shows exactly that. If we go in line 26, we have, line 26 basically depicts this as a plot. So line 26, 27, 28 basically builds as a scatter plot, showing that the association, the positive association between stressful life events and depression score, followed by line 29 and 30, which is Fit2B. And now it's getting interesting, because this is a multivariable model now that shows us two different variables, our life events and our sleep disturbance score. We know the results already from the SPSS output, but here it's just presented in R format. We also see this time around, we see the residuals, we see the median slightly larger, which would render the mean to be a little bit smaller, possibly with some outliers to the negative, which is not much, but a bit. We see again the residuals and the interquartile range. We see again the coefficients. We see the estimate, standard error, t-values, and p-values. Interestingly here, and we knew that already from the SPSS output, the only significant predictor of this association is actually sleep disturbance scores. So sleep disturbance, sleep is actually overriding the signal of stressful life events, render stressful life events as being less, having less weight in the prediction of our depression score. So essentially we have now a strong predictor, and we also have a high level of accuracy. We see here our R squared confirmed, the one we calculated in Excel with 0.8995. And here I just want to bring some aspect to your attention. So we have here a multiple R squared, and we have here an adjusted R squared. These two are inherently different. The multiple R squared is calculating the R squared in exactly the same fashion as we have calculated in in Excel. So we have a total variability, we have a residual variability, we have this explained variability, and now we have the explained variability as a fraction or as a proportion of the total variability gets us the multiple R squared, the regular R squared. Then adjusted R squared is additionally adjusted for the number of variables included. It's not perfect, but it's an attempt to penalize the model for the number of variables included in your prediction. Because arithmetically, when you think about it, the more variables you include in your model, the more variability your model will explain. But that needs to come at a price, because the sky is the limit, right? It's like you basically, by adding too much information, you will run into an overfit of the model, where you're not predicting, you're predicting biased results in a way. So this needs to be penalized, because otherwise you would see erroneously large predictive qualities of a model. So the penalization by additional variables, this is quite commonly, and Excel, for example, by default, so if you have that R squared that Excel shows, that's an adjusted R squared. So, so it's kind of a default setting for most statistical softwares. You have an F statistics. Now you have 2 degrees of freedom in the numerator, because it's intercept and 2 variables, that makes it 3, minus 1 is 2. You have 7 degrees of freedom, because you have 10 entries and you have 3 variables, 10 minus 3 is 7. The p-value is significant at an alpha level of 5% of the overall predictive accuracy of your model. Good. Last but not least, 2 more minutes. Okay. So we have here in line 33, we have plot fit to B. If you plot your model, what you will get from R is quite elegant, because in regression analysis, you will need to run diagnostic plots to understand the dynamics of your residuals, because if you build advanced models, you essentially, if you plan to build advanced models and you want to predict something with a certain accuracy, you need to understand where does my model start to fail? Where do the residuals actually overweigh my accuracy, and what are the downsides and what are the weak points of my model? So these diagnostic plots essentially gives you here an overview of your residuals as a function of your fitted values. And you can look at various ways how to depict that. So these are the standardized residuals as a function of the theoretical quantiles. So you have various ways to look at your residuals and draw inferences about the dynamics of your residuals, and to also test that your assumptions are being met and your model is actually accurately and properly designed. If these residuals are acting out and skewing and changing the accuracy, you will possibly need to do something about it, and you will need to modify variables or group and stratify variables. So there are various ways how to deal with disturbances or like this skewness of residuals. You also see here, for example, you see the leverage of some of the residuals in its more extreme values, where they essentially are to some extent shifting the accuracy of the result. But that's far beyond the purpose of this class. The only thing, keep in mind, you need to add return 4 times to get through the plots when you run the code. But basically, this is the point where you basically just go and select everything in the console. You go on Spotlight, you find text edit, and you're basically building in your document. You're copying your console in, you save it as STAT1021G, your family name, practice lab 5, and enter, and you submit it via Canvas. Thank you very much. Have a nice evening. If no questions.